Hey, good morning, Derek.
Hey, Mohit. Good morning.
Good evening.
All right, I guess I can start. Do you have any comments before I start?
Not yet. Not.
Okay. Can you allow me to share my screen? Thank you. All right, can you all see a reflection seismology slide?
Yeah.
Yeah, okay, good. All right, so today I'd like to talk about, start talking about reflection seismology. This is section 3.3 in the Stein and Weiss session book. And we are going to look at ray theoretical aspects of reflection seismology. So reflections off of interfaces are quite useful, especially if you are interested in seismically probing sedimentary layers. But it's also quite useful for understanding global ray paths. So we will start with a simple layer over a half space, and rather than the refracted or head wave, we will think about the reflected wave this time. So we will cover travel time curves, then we will get into the Dix equation. We will talk about ray tracing in a continuous Earth, and then we will talk about Taupe, or the intercept slowness method. And then in short units, we will look at multi-channel geometry, signal enhancement, and deconvolution. So travel time is the distance over the velocity, and the distance that this reflected wave traveled can be calculated from the Pythagorean theorem. So it's 2 times the square root of x over 2 squared plus h naught squared, where x is the distance between the source and the receiver, and h naught is the thickness of the layer. So we can divide through by the velocity and then square both sides to get the travel time equation. This is a hyperbola that intercepts the t-axis at t naught equals 2h naught over v naught. So you can imagine if the source and the receiver are in the same place, you would just have a vertical bounce back up, and that's why you have 2h naught, because you have the downward leg and the upward leg divided by v naught, and that equals the travel time. Now you could plot t squared versus x squared, and that would have a slope of 1 over v squared. Now, if we're talking about multi-layered structure, for a given ray with a ray parameter p, we can think of tangent of I in the jth layer is equal to x sub j over h sub j. So for instance, tangent of I1 equals x sub 1 over h sub 1. So the horizontal distance traveled in each layer is just solving for x. So x sub j equals h sub j tangent I sub j. And we can double this to get the distance traveled by the upward ray. So x as a function of ray parameter equals 2 times the sum of all horizontal distances traveled by the ray on the downward leg, and that equals 2 times h sub j tangent I sub j for j equals 0 to n, where n is the bottom layer that the bottom reflection. So now let's d sub j be the distance traveled by the ray in each layer. So this is the total distance, not just the horizontal distance. we can use cosine I sub j equals h sub j over d sub j to get the total distance traveled in each layer j as d sub j equals h sub I over cosine I sub j. So this is just a little bit of trigonometry. And since travel time is distance over velocity, the travel time in each layer j is just h sub j over cosine I sub j times 1 over v sub j. We can double this to reflect the time it takes for the upward ray to propagate. So the total travel time of a ray is going to be 2 times the sum of h sub j over v sub j cosine I sub j for j equals 0 to n. Again, n is the bottom layer where the reflection occurs. We can approximate our travel time equation for multiple layers. So we can take t sub x squared and call it t sub x squared for layer n plus 1. And then that equals x squared over v n bar squared plus tn squared, where tn is the travel time through layers 0 through n, and v bar n squared is the RMS velocity for layers 0 through n. So basically it's the average velocity that the ray sees in layers 0 through n. So for reflections off layer n plus 1, so this is layer 2, so reflections off layer 3, we would plot t sub x squared of n plus 1 versus x squared. So this is something you could actually measure in the field. If you have a source here and a bunch of receivers along a line, and that would give you the slope 1 over v bar n squared. And then we would use something called the Dix equation. So the Dix equation says the velocity in layer n is the RMS velocity squared times the travel time to layer n minus the RMS velocity for layer n minus 1 squared times the travel time to layer n minus 1 over tn minus 1. This is an approximation, and it works pretty well for small offsets and non-dipping layers. So v sub n bar squared is something you would measure. V sub n bar n minus 1 squared is something you could measure. Tn and tn minus 1 are also things you can measure. So you can measure all these to get v sub n. Now for a dipping layer, say with an angle of theta, the travel time curve is a hyperbola, but with an offset of 2h sine theta. So if we had a flat layer, we would have a hyperbola if I plot x and t travel time on a downward axis, where the peak of the hyperbola is right at 0 offset. But for a dipping layer, because the shortest distance between the source and the receiver is actually going to be offset a little bit from the actual source, you have a hyperbola with a peak at minus 2h sine theta. So if you see an offset in your travel time curve, then you should realize you have a dipping layer. Now for continuously varying v sub z, so rather than layers, if we just have a continuously varying velocity structure, we just replace things by integrals. So our ray parameter equals sine of I over v, which is a function of depth, and sine sub I equals the ray parameter times v sub z. If v sub z increases continuously, so will sine sub I, and this I, and you get the ray path shown here. And what we will do is we will cover from the source to the bottom out point, and then we will just multiply it by 2. So the layered formula is x sub p So the offset between the source and the ray appearing is x, and that's equal to h sub j tans I sub j, where we sum from j equals 0 to n. And the smoothly varying Earth structure, we just replace the summation by an integral. And we integrate from 0 to z sub p, where z sub p is the depth at which the ray starts turning upward. Now, since tangent of I equals sine of I over cosine I, and sine of I equals p times v of z, then we can rewrite cosine I in terms of v and p. So this is just the trig identity, cosine squared plus sine squared equals 1. And sine squared equals p squared v squared. So we get the square root of 1 minus p squared v squared. And that also equals v times 1 over v squared minus p squared, square root. So then we can take our distance measurement, x, and convert 2 times the tangent of I dz to 2 times pv over square root of v, square root of 1 over v squared minus p squared times v. This simplifies, since we have a v here and a v here, to 2p integral of square root of 1 over v squared minus p squared dz. And if we use slowness, here I'm going to use slowness of u just because this is what the Stein and Weiss session book uses. This is different from the deformation function u. This is slowness, so it's p and eta in a two-dimensional form. And here we are just taking it in the scalar form, so it's 1 over the velocity in any layer. And so x of p equals 2 times p times the square root of u squared minus p squared dz. We can follow a similar series of steps to get travel time. And I won't, this is just algebra here. And then I will say that the travel time equals 2 times the integral of 0 to z sub p of dz over the square root of u squared minus p squared. So if we can write our velocity structure down as a function of z, we can calculate the arrival time and the distance that any ray travels. So that's quite useful. Also, if ds is a unit of length along the ray path, such that dz equals cosine I ds, so z is s is just an arbitrary small length of the ray, then our travel time is just the integral of u of z ds, or ds over v. And we're dropping the 2 in the integral, so we start out with a 2 and then we drop it here because we are going to take the integral from the source to the receiver, so that we don't have to multiply the answer by 2. All right, so that gave some quick formulas for plotting travel time and distance of a given ray, assuming you know a velocity structure. This is in a flat Earth, so this would help be useful in sedimentary layers, for instance. It's not quite applicable for a globe, and we'll talk a little bit about a globe in my second lecture today. So now I want to talk about the Taupe method. And so the travel time along a ray path is the slowness times the distance. So it's the sum of j equals 0 through n, so we're assuming we have n layers, of the slowness in each layer times the distance it travels in each layer, which can be rewritten as the ray parameter in each layer times eta in each layer, dotted with the horizontal distance it travels and the vertical distance it travels. Since ray parameter is constant, we don't have to actually have P sub j. We can just put P for any given ray. And so travel time as a function of P is equal to Px plus 2 times the sum of eta sub j over times h sub j. So this is the vertical travel time, and this is the horizontal travel time. So on a Tx plot, the slope is P, and the y-intercept is 2 times the this parameter, which gives the vertical travel time. So let's call this vertical travel time tau. So we will call tau, which is a function of P, 2 times the summation of eta sub j, h sub j. And we can rewrite eta sub j as 1 minus v squared, 1 over v squared minus p squared square root. And we can write 1 over v squared as u squared. So we can rewrite tau of p as 2 times the summation of the square root of u squared minus p squared square root times h sub j. And just to simplify things, we can also write our travel time, our total travel time, as the horizontal travel time, so the ray parameter times the horizontal distance, plus the vertical travel time, which is calculated with this formula up here. So travel time equals px plus tau sub p, looks a lot like y equals mx plus b. So it looks a lot like a slope and an intercept. And indeed it is. So if I plot travel time versus distance of the receivers from the source, I would get this inverted hyperbola here. At any given point, that's a particular ray, a given point, I can take the slope of this line, and that will give the ray parameter associated with that ray. And the intercept will give tau, which is the vertical travel time. So let's look at an example. For a reflected wave over a half space, if I is the angle of incidence with respect to the vertical, then P equals sine of I over V naught, which is just the definition of ray parameter. And by trigonometry, we can say sine of I equals x naught over 2 times the square root of x over 2 squared plus h naught squared. And then we divide that by V naught to get this formula here. We can do something similar to get the cosine over V naught and get this line here. And then we can calculate the travel time as px times eta h naught. And then we can combine terms, and we get 2 times the square root of x over 2 squared plus h naught squared over v naught, which is actually the hyperbola that we derived before. So using our travel time formula in terms of px plus 2 eta h, we have derived our travel time formula that we calculated before. We can also just derive tau of p. So tau of p equals 2 eta naught h naught, and that equals tau squared equals 4h naught squared times 1 over v naught squared minus p squared. And you can rearrange things to get v naught squared tau squared over 4h naught squared plus p squared v naught squared equals 1. This is the equation of an ellipse. So this is an ellipse with coordinate axes along the tau and p axes. So we can take our travel time versus distance plot. So here's the distance, here's the travel time, and also calculate a tau versus ray parameter plot. And we can also go and calculate ray parameter versus distance. So for this reflected wave here, any given point, the slope here is going to give the ray parameter. So that'll show up here. And the intercept will give tau, and that'll show up here. And the x value is the ray parameter. This here tells us that the ray parameter tau relationship will be an ellipse. And this line here tells us that ray parameter will go from a slope of 0 to a slope that approaches this direct wave, which is 1 over v naught. So ray parameter will go from 0 and it will approach 1 over v naught. And we can look at the relationship between tau of p and x if we rewrite our tau of p again as 2 eta naught h naught, which is 2 h naught times the square root of 1 over v naught squared minus p squared. And then we can take the derivative to find that d tau dp equals negative x of p. And this just equals 2p h naught times the square root of 1 over v naught squared minus p squared. Now, if I plug in ray parameter equals 1 minus v and tau equals 0, x here goes to negative infinity. That makes sense if I think that if ray parameter is 1 minus v naught, then what I've done is basically I've taken my ray parameter and I've gone to infinite distance. And what we'd see is basically a reflected wave that looks a lot like our direct wave. And so in the limit, as x goes to infinity, ray parameter goes to 1 over v naught, and tau becomes 0 because the intercept of this starts to approach being 0. All right, let's look at another example. So let's consider a reflected wave over a half space. Tau of p equals 2 times the summation of eta sub j h sub j. Right, this is just our definition. And since we just have one layer, we can write it as 2 times the square root of 1 over v naught squared minus p squared times h naught. Squaring this, we get tau squared equals 4 h naught squared over v naught squared minus 4 h naught squared p squared. Multiply this by v naught squared to get this equation here. And then we can rearrange and we find our ellipse again. And we can note that the ellipse intersects the tau axis at p equals 0. So this is right here. This equivalent in our travel time distance plot is right here. So this is our vertically incident ray. And our ray parameter here is just the slope of this line. Our slope of this line is 0, so our ray parameter is 0. In general, the d tau dp slope is going to be minus x of p, which will equal this equation here. And again, if p equals 1 over v naught, x goes to infinity. So as this should be out to infinity right here. And this would correspond to this point on the tau p plot. And what I would encourage you to do is to look at this plot and see if it makes sense. It takes a little bit of intuitive work to build an understanding of these plots. All right, so now let's do a head wave. So our head wave is going to follow this relationship here. And our tau value is just going to be this part of the equation. And so our travel time equation is x over v1 plus tau sub 1 and dt dx, which equals p, equals 1 over v1. So for all our refracted waves, we have a constant value of p. We can plug this in the equation for tau sub p and recall that we only have one layer, so n equals 0. And that tells us that tau of p equals 2 h naught v naught times the square root of v1 squared minus v naught squared. And this turns out to be x sub c, which is the critical distance at which the head wave first appears. So here's our head wave on our travel time versus distance plot. We can see it has a constant slope. So if I plot the ray parameter, which is this y-axis here, versus distance, I have a straight line. The y-intercept is going to be a constant value, and that is going to be at the critical distance. So this here, if I go up here, this is going to be x sub c. So since this was a little confusing, I want to do a recap. So for a reflected wave, we have an inverted hyperbola, and p goes from 0 to 1 over v naught. And in tau p, it goes from tau equals 2 h naught over v naught right here to tau equals 0 for p equals 1 over v naught. So this is for infinite distance, and this is for 0 distance. For the direct wave, which comes in following this slope here, it has a constant intercept and a constant slope. So it just plots as one point on our tau p plot. And that's at tau equals 0 because the y-intercept is 0 and p equals 1 over v naught. On our ray parameter versus distance plot, p is constant, it's 1 over v naught, so it just plots as a straight line. And so it looks a little bit like the head wave. Finally, the head wave, it plots like this on our travel time distance plot, our TX plot. It's got one y-intercept, so it sits here on our tau p plot, and on our ray parameter versus distance plot, it plots as a line that starts at the critical distance, x sub c, and then goes off into infinity. For multiple reflections, the tau p formula is also of the formula that produces an ellipse. And what you just see is smaller and smaller ellipses. So here's the first refracted wave off layer 1. Here's the second refracted wave off layer 2. The third refracted wave off layer 3. H1 is the first head wave. H2 is the second head wave. H3 is the third head wave. This is our distance versus travel time plot. So this actually shows you the inverted hyperboles and then the various head waves. And then for continuous structure, replace the summations by integrals. So tau of p is going to be just the integral of 0 to z of p, where z of p is again the turning depth of the square root of u squared of z minus p squared dz. All right, so that was tau p. And now I want to look at multi-channel geometry and how we might enhance signals. And this is primarily of use to active source seismology. And these are the basics of topics that you would cover in an active source seismology course. And here I'm in like 10 minutes, I am going to cover something that would probably be covered over several days. So it's just the briefest overview. So to increase the signal to noise ratio, we often look at data in terms of gathers. So for instance, if we have a source at 10 and a receiver at 6, a source at 11 and receiver at 5, and a source at 12 at receiver at 4, we can categorize array paths by source location, receiver location, the midpoint, so the point at which they bounce, or the offset, so the offset of 4, 6, or 8. We can plot our different source receiver geometries on this plot here of source versus receiver. The midpoint falls between the receiver and the source. The offset is the source minus the receiver. And then we can consider different ways to reduce noise. So we can do a common receiver gather. So basically sum all the data that's observed at one receiver from multiple sources. We can do a common source gather. So sum the data from one source observed at multiple receivers. We can do a common offset gather or a common midpoint gather. And the common offset gather and the common midpoint gather are what is often used. Common offset gathers are handy for small scale projects, since in the travel time equation, x and v naught are constant. So this is a good approach for finding the top of a near surface layer like bedrock. In industry, typically we do common midpoint gathers, and our goal is to find a way to suppress head waves, direct waves, surface waves, air waves, and multiple reflections, and just get the primary reflection. So we just want this up and down wave. So a reflected wave variation in travel time with offset is given by the normal move-out equation. So T of x minus T naught, where T naught is the direct source to receiver, so where I just have the source and receiver in the same location, is going to be 2 times the square root of x squared over v bar squared quantity squared plus T naught squared minus T naught. So again, v bar is the RMS velocity, so the average velocity that you see. So what you might see if I have a source here and then receivers at D1, D2, D3, D4 is arrival times following a hyperbola. And the curvature of the hyperbola is going to be a function of the velocity. So here I show for velocity V1, V2, and V3. And actually V2 fits the velocity quite well. And what we would do is we try different velocities and stack the data from multiple receivers and see what velocity causes the largest peak. And that calculates the velocity at which this reflected wave is encountering. This gives us the RMS velocity to that bounce. So what we do is we correct things along a hyperbola, and then we get a straight line for reflections, and for head waves and direct waves, these do not align well. So what we pay attention to are the relatively straight lines. So here's an example of stacks of multiple layers. So these are seismic sections. Here, the distance is 0 here, and X increases as we go upwards, and T increases to the right. And we can stack each layer, and we find this sort of velocity structure. We can stack different midpoints. So we can stack midpoint 1, midpoint 2, midpoint 3, and this forms a structure shown here by A, B, C, D, and E that actually looks like the layer in question, as if the source and receiver were directly over the layer. So what this does is it takes multiple source receiver paths and stacks it down into one data by midpoint. And that adds, and that augments the data. So here's a real life example. Here's a migrated seismic section across the Peru Trench. And you can see structure in here. It still takes work to interpret these. And personally, I'm not an expert in this. I don't do active source seismology, but this is a geologic cross section that one might develop from this seismic section. Of course, if the layers dip, there will not be a common midpoint, but generally it works pretty well. All right, there are other ways to enhance signal other than stacking. So we can remove undesired waves. We can do static corrections. So when we have a strongly varying velocity structure in the near surface, we'd apply a time correction to each seismogram. We can mute parts of the data where we see direct waves, surface waves, or other sorts of waves that we don't want to see. We can group receivers along certain common characteristics. So for instance, we can group receivers such that we don't get these short wavelength waves. And we can do velocity filtering. Here we suppress waves with undesirable wave number angular frequency traits. Here's an example of muting. So these waves here are surface waves, and we don't want them, so we just erase this part of our seismograms. The book says deconvolution, but this is not deconvolution. To do velocity filtering, we need to transfer things to the frequency domain. So we do a Fourier transform, and if we have a function of travel time, we can convert that to a function of frequency. If we have a function of distance, we can convert that to a function of wave number, or we could do both at once. So we convert u of x of t, this is our displacement now, and to capital U of k sub x and omega. So what we typically would do is plot k versus frequency, and then decide what is the k versus frequency band that contains unwanted signals. So this unwanted signal contains surface waves, air waves, scattered near surface waves, and side wind noise waves. So these are lower velocity waves. And what we would do then is we convert this to U of K and omega, and then we just damp this all to 0, and then we convert it back. So here's the raw Schutt record, and here it is with the FK filter. You can see it's quite different. Slant stacking, sometimes it's useful to transform data to the Taupe domain and remove waves with undesirable move out. So to convert things to Taupe, we basically pick a slope and an intercept and then stack all the data along that slope and intercept. And here are 4 examples of these 4 lines. And we would do this for all values of P and all values of tau. Here's an example. Say we want to remove the surface wave. So what we do is we do a Taupe transform on this data. We get this, and then we cancel out this energy here, and then we convert it back to our travel time versus distance plot, and you can see the surface wave has been removed. So slant stacking the math, U bar is the displacement in Taupe space. Now deconvolution. So if I have a source and receiver over a geologic section such as this, and I input an input pulse that looks like this, the seismic trace will look like the input pulse times a bunch of impulse functions that are due to the impedance variation between each layer. And so what we see is a seismic trace, which is the reflector series convolved with the input pulse. So our observed, let me see. Yeah, our observed trace is the input pulse convolved with the, I forgot what it's called, really, the reflector series. And this is, you can get a time series analysis class that will go into this, but this convolution is written like this. And we can also write it in the frequency domain, and then frequency domain, it's just a multiplication. To give you an idea what a convolution is, if it's a flip and a summation. So I take 2 functions, f of t and g of t. I flip g of t, and then I slide the second function past the first. I take the integral of the area under both functions and plot this as a function of how much the function has been slid over. This is kind of complicated in the time domain. In the frequency domain, it's just a multiplication. So here's an example. And the black line shows the convolved value. Another thing we can do is we want to, if say we're doing an oceanic deployment, we want to create a spiky as possible input function. So if we compare our single air gun to a 7-gun array, the 7-gun array actually creates a spikier input function, which is ideal. to deconvolve a signal, we want to identify an operator w of -1 of t, such that when it's convolved with the source, it produces a delta function. So w -1 of t convolved with w of t equals, now this is a Dirac delta function, which is an infinite spike with 0 width, but we can just think of it as a spike. Then I can take this deconvolving function here and convolve it with my observation s of t. And since s of t is w of t convolved with r of t, then when I convolve w -1 of t with w of t, I get a delta function times, or convolved with r of t, which is just r of t. So what that means is, if I've calculated w -1 of t properly, I've removed the input signal and I just get the response of the rocks. In the frequency domain, we can calculate capital W of omega at times W of omega, and that equals 1, since the Fourier transform of the delta function is 1. So here's an example. Here's a seismic section before and after deconvolution. You can see it affects the traces a bit, but it doesn't produce anything particularly better. Another thing we can do to augment our signals is cross correlation. So here's an example with a vibro-sized truck. So this is a truck that inputs a signal, and it can look like a sweep signal as shown here. And then we observe the energy here. And what we would see is something like this, where we see multiple reflections and they're all stacked together. And it's kind of hard to make sense of where reflection 1, reflection 2, and reflection 3 are occurring. So what we do is we cross correlate this master signal and with the reflections. So we cross correlate, which means we take this, shift it, multiply it with the signal, shift it again, multiply it with the signal, and we see where we get the peaks and troughs, and that tells us where R1, R2, and R3 are. And probably the most widely used process in active source seismology is migration. So imagine we have a point diffractor and we have a source here. The point diffractor will create a hyperbola of energy. So if I have one point here, create this diffraction hyperbola. And what we would do is we use something called Kirchhoff migration, which would take all the energy in this hyperbola and stack it into one point. So we basically take this hyperbola and then we stack all the energy right here. That is a useful way to process active source data. All right, we are going to take a 10-minute break and I will talk about ray theory in a spherical Earth, and I will also answer any questions that you have. So I will be back in 10 minutes. All right, it's time to start the next lecture, but before I do you have any questions on what I just covered? I think the Taupe stuff takes a little bit of work to understand. The rest is just equations that are developed using algebra and then the relationships that we went through yesterday in that sort of summarizing lecture. So any questions? All right, I will start the next talk. All right, so we primarily talked about ray theory in a flat Earth. And this is useful for short offsets in terms of meters or tens of kilometers even. But when we want to talk about the whole Earth, we have to take into account that the Earth is a sphere. So if the geometry is greater than about 20 or 30 degrees, so that means the source, if I take the source location, so the earthquake location, I go to the center of the Earth, and then I go to the receiver, I drew a wedge through the Earth, and that distance can be measured in degrees. And if that distance is more than 20 or 30 degrees, then we need to use spherical geometry. So for instance, Snell's law in spherical geometry, if I consider a ray path in red, and at point A, we can use Snell's law. So sine of theta 1 over V1 equals sine of theta 1 prime over V2. Now we will note the right triangle is formed by D, R1, and R2. So here's D, here's R2, here's R1. And since sine is opposite over hypotenuse, sine of theta 1 prime is D over R1. Sine of theta 2, so here's theta 2, is D over R2. So we can set these both equal to D. So that tells us R1 sine of theta 1 prime equals R2 sine of theta 2. Now we'll multiply both sides of Snell's law by R1 to get R1 sine of theta 1 over V1 equals R1 sine of theta 1 prime over V2. And then we will note what we did in the last slide, that D equals R1 sine theta 1 prime equals R2 sine theta 2. And then we can set R1 sine theta 1 over V equal to, and we will replace this R1 sine theta 1 prime by R2 sine theta 2. And that gives us Snell's law in spherical coordinates. So we have R1 sine theta 1 over V1 equals R2 sine theta 2 over V2. So as I go from one layer to another layer in the Earth, we have to multiply by the distance that we are from the center of the Earth. In terms of slowness, so again, U is representing the 1 over the velocity. We can just write 1 over the velocity as U1, 1 over velocity 2 as U2, and these are equal to the ray parameter in the Earth. So we have a slightly different ray parameter here. And this corrects for the fact that as the ray gets closer to the center of Earth, its orientation normal to the spherical interface changes. So it just means that because we are dealing with spheres rather than flat layers, we have to take into account the fact that theta 1 prime and theta 2 are actually different angles. We can also consider two nearby rays. So here's ray 1, here's ray 2, and we're assuming that they're quite close to each other. So we have a triangle. The hypotenuse is given by r naught d delta. The opposite angle or opposite side is given by v naught dt. And this distance here is the distance that the ray travels in travel time dt. As these rays get closer together, the adjacent and opposite side to angles I approach linear. Hence, in the limit, sine of I equals v dt, v naught dt over r naught d delta. Rearranging, we get dt d delta equals r sine I over v. Since ray parameter is r sine I over v, this implies p equals dt d delta. So you might recall for a flat earth, p equals dt dx. Here, p equals dt d delta. So thus, for a plane wave, p equals 1 over c of x, where c of x equals 1 over d delta dt, or dt d delta. If we assume that energy leaving an earthquake hypocenter is approximated as being uniform by angle I, and we will see that that's not the case in a couple of lectures, but for now we will assume that, then we will assume that the number of rays that arrive per unit distance is going to be proportional to the amplitude of the seismic waves that we observe. So amplitude is proportional to di, d delta, where I is the takeoff angle of each ray. So P equals R sine I over V, which we've just shown. And that equals dP d delta, which P equals R sine I over V. So dP d delta equals R over V cosine I di d delta, which means that dP d delta equals d squared t d delta squared. This is just because P is dt d delta, and this is proportional to di d delta because we have this term di d delta in the dP d delta term. So the dP d delta derivative is proportional to the amplitude, and we'll see why that's relevant shortly. So like we did for Cartesian geometry, we can also describe travel time in terms of the slope and intercept. Except here, rather than P times X, we have P times delta. So some useful relationships are dt d delta equals P, and d squared t d delta squared equals dP d delta. So P is simply the source, the slope of the t versus x line here. And if I plot t versus delta, then we get the ray parameter for a spherical Earth. And tau is again the tangent to the curve. Now, travel time distance relationships are slightly different for a spherical Earth. Say we have a constant velocity. So say we have a flat Earth with a constant velocity. We just see a TX diagram that looks like this. However, in a spherical Earth with a constant velocity, straight lines do hit the surface, and they hit the surface at shorter and shorter times as you go to greater and greater x. So what this means is d squared t d delta squared, which equals dp d delta, is less than 0. So this slope here, the second derivative of this slope is going to be less than 0. We can do some simple math to show that the travel time, which is the slowness times the ray length, is going to equal 2 times r naught, which is the location of the epicenter, to rp, which is the deepest point on the ray path, zeta squared dr over r times the square root of zeta squared minus p squared. And so this is similar to what we found for a flat Earth, except zeta equals r over v. And in this formula, tau sub p, or tau of p, is going to be similar. It's going to be zeta squared minus p squared square root dr over r. So the most common case is that as p decreases, x or delta increases. And this is simply because p equals r sine I over v. So as p decreases, we get a smaller and smaller takeoff angle, which means it's increasingly vertical, and more vertical rays travel farther than more shallow rays. So this ray here is more vertical than these rays here. So typically we see travel time versus distance. Again, d squared p or dp d delta is going to be less than 0. So you have a slope here that is going downwards. In this slide, I kind of say the same thing. As p decreases, so p decreases from 1 over v naught to 0, the distance that the ray travels increases. However, when we have a triplication, we have an increase in the velocity gradient. So here's velocity as a function of depth. And that will cause a situation where x decreases when p decreases. This is called retrograde motion. So as p decreases, x also decreases. So dx dp or d delta dp is greater than 0. And prograde motion is where you have a simple velocity gradient and x increases as p decreases. So for this situation where we have prograde and prograde motion, we have retrograde motion in the high velocity gradient section, and that causes x to decrease. So typically what we have is we have prograde motion from A to B. So these are the rays that turn in this top layer. Prograde motion from C to D. So this is prograde motion in this bottom layer, and the arrivals are C to D. And retrograde motion from B to C. And these are arrivals that turn in this layer here. On a TX diagram, we get this triplication here. So A to B is prograde, C to D is prograde, and B to C is retrograde. If I plot dp dx, I get this. And where this slope is infinite, we would also have high amplitudes because the slope is proportional to the amplitude. Each of these segments in the TX diagram is called a branch. So this is the AB branch, this is the CD branch, and this is the BC branch. These points B and C are called caustics. And by ray theory, they would have an infinite amplitude. In practice, they do not. We can also plot this in terms of X versus P rather than P versus X. And we get prograde, retrograde, and prograde motion here. Here's what a triplication looks like in tau P space. So in this case, d squared tau d delta squared is greater than 0 for prograde motion. D squared tau d delta squared is less than 0 for retrograde motion. And then back to greater than 0 for prograde motion. So the changes are a little more subtle here. So and then the blue circle shows the prograde, the yellow circle shows the retrograde, and the red circle shows the prograde again. So triplications imply an increase in the velocity gradient, and within the triplication, 3 rays will arrive, right? So if at a given distance, I have 1 ray, 2 rays, 3 rays arriving. At the edges, caustics will have high amplitudes, and triplications will have prograde, then retrograde, then prograde motion with decreasing P. At caustics, dP d delta, like right here and right here, is infinite, which would cause high amplitudes. And we can make things easier to plot is if we convert our t to t prime, where t is equal to t minus some reducing velocity times distance. Here's an example. This is a triplication showing a low velocity layer at 300 kilometers depth and a high velocity layer at the transition zone, mantle transition zone here and here. And A shows the triplications lines without a low velocity zone. So that's this right here, just having the high velocity jump right here. And B is without a lid. So rather than going to higher velocities, it just goes to low velocities and then has a larger jump. So these are actual plots of real seismographs. Now, another feature we might get in TX diagrams or T delta diagrams is a decrease in velocity causes rays to turn more vertically, creating a shadow zone. So here, rather than rays turning upwards, they turn downwards. And then when they turn upwards again, we create a shadow zone. So in our TX diagram, we will actually have a plot, an area where we receive no data. On a tau P plot, it'll look like this. We can actually have a ray produced in a low velocity zone be trapped. So a typical place is in the SOFAR channel in the oceans, where we have water depth versus velocity between 500 meters and 1,000 meters in depth, has a velocity low, and that causes rays to just travel in this channel. So the shadow zone will show up as a gap in tau delta, tau P, and P delta. So let's look at the requirements for a shadow zone. So we will consider a downgoing ray. For it to turn upwards, its angle with respect to vertical must continue to increase. So for it to turn upward, I has to go to larger and larger values. As it gets deeper, it gets closer. This would say gets, not guessed. Closer to the center of the Earth, so R decreases. So I increases, R decreases. So for a ray to turn upwards, dI, dr has to be less than 0. Let's consider what this means for a velocity structure where v is a function of depth. We'll start with the definition of ray parameter on a sphere. This implies sine of I equals PV over R. We'll differentiate both sides. and we get di dr cosine I equals P times 1 over R dV dr minus V over R squared. We will note that P is equal to R sine I over V. So we have this relationship here, and we can simplify that by multiplying through by V, and we get sine of I times the quantity 1 over V dV dr minus 1 over R. And if we divide through by the cosine, we get di dr equals tangent I 1 over V dV dr minus 1 over R. This will be positive when dV dr is greater than V over R. And that means di dr will be positive, and therefore our rays will be directed downwards when dV dr is greater than V over R. So that is our criteria for producing a shadow zone. Here's a real example. Here's a shadow zone, and here's a shadow zone. For instance, this one here is due to this low velocity feature right here. All right, and then finally, if we want to simulate the effects of a spherical geometry, but we've created a model that is in a Cartesian geometry. So we've created a tomography model with rectangular pixels, and we want to convert it to a spherical geometry. We will do that in terms of fractional radius. And what we will do is derive the depth at which a layer in a flat Earth model would have to be moved in order to be equivalent to a spherical model at a given depth. And that is given by Z of F equals minus A natural log of R over A. So for instance, if I have something at the surface of the Earth, so at the depth of 0, the Earth flattened depth is the same as the spherical depth. If I have something at 100 kilometers depth, the Earth flattened depth is 100.8 kilometers depth. So in the uppermost mantle, it really doesn't play a role. So again, even at 1,000 kilometers depth, now we're talking about 9%. So it's starting to become significant. And here in the lower mantle, at a depth of 2891, the Earth flattened depth is significantly different from the true depth. So what we would do is take our depth in our model, and then we would expand the bottom to match these depths, and that would be more accurately accurate for a spherical Earth. We also can do transformations for seismic velocities. So for P wave velocity, the flattened velocity is A over R times the spherical velocity. And for shear velocity, it's A over R times beta spherical. So if we want to go from the flattened to spherical, we have to multiply by A over R or R over A, depending on what direction we're going. This does start to become significant below the MOHO. There's also transformation with density, and that is R over A to the 5th power. So that is quite significant. These transformations are exact for SH motion, but approximate for PSV. We do it because sometimes it's easier to work in Cartesian coordinates than spherical coordinates. But really, if you're going to work below the mantle transition zone, you want to actually start thinking about doing your models in spherical geometry. Here's an example. So at the core mantle boundary, if I have a P wave velocity of 12 kilometers per second, I would extend it in depth and increase it to 23 kilometers per second. Or if I had a flattened model, I would want to go this direction here. So if in a spherical Earth model, VP equals 8 kilometers per second at 100 kilometers depth, the depth in a flattened Earth model would be 100.8 kilometers, and the velocity would be 8.12 kilometers per second. All right, and that's all I had for you today. So I thought that you guys could work on the homework and ask me any questions in the next 25 to 30 minutes.
Dr. Schutt, can I share my screen?
Yes, please.
Oh, I had just one question regarding these SKS, SKSS, SSS. What do these things mean? Like, is this just a naming, or does it mean something specific?
It means it describes the path that the rays have traveled through the Earth. So an SKS starts out as an S wave in the upper mantle, travels through the outer core as a P wave, and then travels up back through the upper mantle as an S wave. I'll talk about that tomorrow.
Okay, okay.
So that's a good question, yeah, because that's really not explained there.
Okay. So these are interpretations, right?
I'm sorry, what did you say?
Are these interpretations? I mean, these could be something different from what it was interpreted, or are these 100% correct?
So the SKS arrival time is predicted for a radially averaged Earth model, and then you would match your seismograms to the predictions, but your predictions could always be wrong.
Okay, yeah.
So, yes.
Okay, you said that these are multiple reflections from different places in the Earth's crust, or Earth in different layers of the Earth. I was just wondering if you just look at these pictures, which ones are the which time-wise? I mean, which one are the first ones and which ones are the later ones? Like, just if you interpret this picture, how would you interpret this picture?
So these are Rayleigh waves that have traveled multiple times around the Earth. They've crossed as a surface wave. The R1 wave is the direct earthquake to station path.
Okay.
The R2 wave has gone around the backside of the Earth.
Okay.
The R3 wave has gone from the earthquake to the station around the Earth once, and the R4 has gone around the backside of the Earth once.
Okay.
So the Y value on your Y-axis is the time, and the first plot goes from 0 to 3 hours, and the second plot goes from 3 to 6 hours.
Okay. So these are all Rayleigh waves. There's no other wave in this one. Or...
No, these are just Rayleigh waves. You can see some earlier waves in under the R1 wave. So that.
Okay. But these are not Rayleigh waves, or are these Rayleigh waves as well? So these early waves.
No, those are body waves.
Okay. This Z here is it the depth?
Yes, it is. Yep.
Okay. Can you please tell me once again what this theta means here?
So theta is the dilatation, and it's the trace of your strain tensor. So it's E11 plus E22 plus E33, which is du1 dx1 plus du2 dx2 plus du3 dx3.
Okay. Okay. And I don't have these slides right now. So regarding today's lecture, can you please explain what that eta means? Not regarding these slides, but regarding today's lecture.
In today's lecture, theta just represents the angle of
Eta.
incidence.
I mean, eta.
Oh, eta represents the 1 over the vertical apparent velocity. So if I look at the velocity a wave travels in the vertical direction, eta is 1 over that.
Okay. And also, what's the difference between T and tau? What was that difference? Just the notation.
So tau is the vertical travel time that a ray takes,
Okay.
where T is just time in general. And travel time T is a function of P times X, so your ray parameter times your horizontal distance plus eta times H, which is your vertical slowness times your vertical distance.
Okay. Okay, thank you so much.
Mhm. Any other questions? If not, I'd recommend working on homeworks 1 through 4 and seeing if you can do them. Any questions? All right, if not, I may leave 10 minutes early, and I will be ready tonight with our next tutorial. All right.
Okay, thank you.
Yes.
Thank you so much. Have a good night. That's what I say.
Good night.